Welcome back. So today we're going to finish off chapter 12 on geometry by talking in a little more detail about points and lines, points, lines, and angles. Um, so points are locations on a plane, and a plane is an infinitely large flat surface. So think of like a sheet of paper that extends forever. That's a plane. Two points that lie on the same line are called collinear. So here's an example of 2 points A and B that lie on the same line. And we would call this line the line AB, and we would denote it like this with AB with these kind of line with two arrows on the ends. So that's telling me that this line extends forever in both directions. And lines in this text are going to go on forever. If they don't, we're referring to them as line segments. So for instance, this shorter piece that doesn't continue on forever is the line segment AB and is denoted without arrows on the top. Likewise, if it continues in just one direction, like this line segment, what we call this array. Oops, sorry, and this is CD. And we put the arrow is going in the direction. So if it goes from C to D, so that the arrow is going in the direction of where the arrow is going for the line. So C should be the terminal point of the ray, and then D should be the direction the ray is pointing at. Okay, so a line for us is going to continue on forever, and two lines are parallel if they never intersect. Likewise, two line segments are parallel if their extensions never intersect. So if we were to extend them on to go on forever as actual lines, they would never intersect. So we write that these two lines M and L are parallel by using these double vertical bars. So this means that the line M is parallel to the line L. Of course, if M is parallel to L, then L is parallel to M, so you can write that either way. Okay, so a couple of properties that we have involving points and lines. So for each pair of points on a plane, there is a unique line that intersects them. So as for any 2 points that I write down, there is exactly one line that connects those 2 points. And if I have a line L, so that's what this one is saying, is if I have 2 points A, B, then I can draw a line in between them. This property 2 is stating that if I have a line, let's call it L, and I have some point P that's not on the line, then there is just one line that I can draw that goes through P and is parallel to L. So there's exactly one. Okay, so this gives us 2 different sets of criteria that we can have and get a unique line out. So one is if I have 2 points, I have a unique line that passes through them, and then if I have a point in a line, I have a unique line that's parallel to my original line. Okay, so moving on to angles. An angle is the union of 2 segments or rays. We can have them be rays as well. With a common endpoint. And this common endpoint we usually call a vertex. For instance, in this picture we have here, this is the angle ABC, and I would denote this angle with this little kind of angle symbol, and it's the angle ABC. It's also the angle, I could also write this as the angle CBA. That's totally fine. The order doesn't matter too much, but what does matter is that the vertex of the angle should be in the middle using this notation. So notice that either one of these is fine, but writing this angle as angle BAC is not correct, just because it causes confusion. So B, the vertex should always be in the middle here. Okay, so here we call this piece the exterior and this kind of inner piece the interior. And the interior part is convex, which basically means that what convex literally means is that if I, on this interior piece or on the piece that's where this is convex, I have, if I draw any 2 points in this piece, I can connect it with a line that stays completely in the piece. So here on the interior, I can connect, or I can write 2 points, and I can connect them with a line that stays on the interior. That is not true of the exterior, because if I put these 2 points here, the line that would connect them would also pass through the interior or stay completely in the exterior. So this exterior piece we call concave, and the interior piece, this is convex. Okay. Usually these refer to larger shapes, these terms, but they're kind of in relation to an angle. Okay, so this brings us to the measure of an angle, and we denote this by, so if we're talking about the angle ABC, like this one, to talk about the measure of the angle, we would put an M. We use this notation M of ABC, or of angle ABC. And we call an angle acute if it's less than 90 degrees. So it is kind of a skinnier angle than the 90-degree angle. It's a right, we call it right if it is 90 degrees exactly. So in this case, my 2 line segments M and L are perpendicular. And another way to write that 2 line segments are perpendicular is using this notation. M is perpendicular to L. So we draw this little kind of image of 2 perpendicular lines. This reads like M is perpendicular to L. And an angle is obtuse if it is more than 90 degrees. So meaning it's open wider than the 90-degree angle. Okay, a few more bits of terminology. So we call 2 angles congruent if they have the same measurement. So that means that the measure of, say, angle, this first angle looks like BAC, and the second angle is DEF, this is an E. And so if the measures of these 2 angles are the same, they are congruent. And we can see that in this picture by basically, if I were to pick up this angle DEF and rotate it and kind of move it over, it should lie exactly on top of the angle BAC. 2 angles are supplementary if when I add their measurements, I get 90 degrees. So, if they add to 180 degrees, I'm sorry. So for instance here, if I add the measure of angle 1 and the measure of angle 2 here, I should get this whole 180 degrees. So measure of angle 1 plus measure of angle 2 should be equal to 180 degrees. And they're complementary if their sum is 90 degrees. So in this example on the right here, the measure of angle 3 plus the measure of angle 4 should be 90 degrees. Okay. So there's often this picture of what happens. So one way of telling if two lines are parallel, like L and M here, is to draw a transversal in between them and talk about the angles in relation to the transversal and the original two lines. So let's say we have this line L and this line M, and we want to know if they're parallel. One way we can do that is by drawing this blue line, which is called the transversal. It transverses these two lines M and L. And there's a little terminology we can talk about. So when I do this, I form a bunch of different angles, right? And I form an angle here between L and T, and another one here between L and T. In fact, there's 4 angles that kind of happen between L and T, and so I've labeled them 1, 2, 3, and 4. And the same thing happens with M and T, right? I have 4 more angles, 5, 6, 7, and 8, that are created when I draw this transversal. And so we have a little bit of terminology to help describe these angles. Angle 1 and 5, so if they kind of look like they're corresponding, they have corresponding relationships to the transversal, they're called corresponding angles. So for instance, angle 1 and 5 are corresponding. Also, angles 2 and 6 correspond with each other, but 2 and 5 don't correspond, right? But 3 and 7 do, and 8 and 4. Those are my examples of corresponding angles. 3 and 5 are what we call alternating interior angles. Different color here. Or sorry, alternate interior angles. So as you would guess, these angles should be interior. So meaning interior in the interior of L and M. And we want to choose the alternating ones. So that's 3 and 5 are alternating interior angles. Also, 4 and 6 are alternating interior angles. Those are my 2 sets of alternating interior angles for this diagram. And the reason we have this terminology to describe these angles created by the transversal is because if I know the measurement of these angles, it can tell me whether or not L and M are parallel. So let's say we have 2 lines, L and M, and they're intersected by a transversal, just like my picture up here. So then L and M, they're going to be parallel. That's, remember what this notation means. If and only if the corresponding angles are congruent. So meaning they're the same size. So for instance, up here, L and M are parallel. These 2 lines are parallel if these 2 purple angles are the same measurement. Or if these 2, the angles 2 and 6 are the same measurement. So for instance, so this means the measure of angle 1 is equal to the measure of angle 5. Technically, the way this is worded is, I think it's saying that all of the sets of corresponding angles are the same size, all the pairs. So all corresponding angles are congruent, but I think we actually really only just need 1 pair of corresponding angles to be congruent. So it would suffice to just say that the measure of angle 1 is equal to the measure of angle 5. I wouldn't also have to show that the measure of angle 2 is equal to the measure of angle 6. I think technically we probably want to do a little more work to show that that's true, but it is. Okay, another way to show that 2 lines are parallel is, so L and M are parallel if and only if, oops, sorry, I meant to do this. L and M are parallel if and only if their alternating interior angles are congruent. So if this angle for 3 and 5 are the same length. So notice those are not the same thing as the corresponding angles. but showing that measure of angle 3 is equal to the measure of angle 5 would also be sufficient to showing that those two lines are parallel. Okay, and the reason why we bring these up is it's actually, we would use these two properties to show, actually I think we just need property 2, that the measure of the interior angles of a triangle sum to 180 degrees. So let's look at this triangle ABC here, and we'll show that this is true. So the way that we would show that this is true is we want to extend the lines that create this triangle kind of on infinitely. So we just have these line segments, so we're going to continue this line segment AB on forever. Pretend it keeps going. Let's continue the line segment BC on forever. And let's continue the line segment AC on forever as well. Or at least a little bit further. Okay. Great, so we're just continuing the lines of that form the sides of this triangle on forever and kind of looking at what angles are formed when we do that. So when I do this, let's call these interior angles of the triangle. Let's call them 1, 2, 3. Okay, so what I want to show is that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180 degrees. So let's look at these, and then let's look also at a couple other angles. Oh, and there's one other piece that I'm going to need here. Okay, so we've continued these line segments on, okay? And so that should be fine. And notice, so remember, if I have a line and I have a point that's not on the line, I can draw, there's one line that's parallel to it, right? So let's look at, we have this line segment, and let's look at this point at the point B. So if we consider just this line segment through AC, or sorry, the line through AC and the point B, there's a unique line that I can draw through B that's parallel to AC. So I'm going to draw that line. Okay. And so now there's a couple different angles that I'm going to want to look at. So let's just label these two angles. We could label all my angles here if we wanted to, but these are the only other two that I'm going to need is angle 4 and 5. Okay. So now what we want to do is we want to use what we know about alternate interior angles and such. Okay, so one thing we should notice first is that angle 1 and angle 4 should be congruent. So let's label these so we see angle 1 is here and angle 4 is here. And they should be congruent because they're alternate interior angles. So angle 1 and angle 4 are congruent interior angles. Also, angle 2 and angle 5 are alternate interior angles, so they're also congruent. So writing this out, this means the measure of angle 2 should be equal to the measure of angle 5, and the measure of angle 1 should be equal to the measure of angle 4. Okay, that's what those two statements mean. Also, just by looking at my picture, I can see that the measure of angles 4, 5, and 3, or 5, 3, and 4, whatever order you want to say it, the measure of these three angles should add to 180 degrees, right? Because um, they are summing up to give me the angles that fill up that get me all the way through to this flat line. Okay, so let's go ahead and we have and measure of angle 5 plus the measure of angle 3 plus the measure of angle 4 should equal 180 degrees. And now all we have to do is notice that we have already said that the measure of angle 5 is the same as the measure of angle 2. Oops, sorry. Well, my colors are off, but it's not a big deal. I'll put this in the corresponding color. This is equal to the measure of angle 2. And the measure of angle 4 is equal to the measure of angle 1. So this should give us now, if we just substitute these things in, exactly what we wanted, which is the measure of angle 2 plus the measure of angle 3 plus the measure of angle 1, sorry, is equal to 180 degrees. And remember, oops, that is exactly, oh my goodness, that is exactly what we wanted, right? So that the sum of those interior angles of the triangle is 180 degrees. Great. So if we were to continue on looking at section 12.5, there are similar results that extend to all parallelograms or regular n-gons. I'm sorry, I guess not parallelograms, polygons is what I meant to say, regular n-gons. And so if you see on page 607, I know if I have a triangle, so something with 3 sides, my sum should be 180 degrees. If I have a 4-sided polygon, so like a rectangle or a square, then my angle sum should be 2 times 180 degrees. If I have a 5-sided n-gon or a pentagram, then the sum of my angles should be 3 times 180 degrees, and so on. This trend kind of continues. So you can see this on page 607, and they tell you a little bit about where this result comes from. But the sum of the interior angles, these ideas do generalize to larger polygons, not just triangles. And this is kind of where that starts. Okay, so I also wanted to point out on page 595, there is a nice table with all of these terms referring to angles that we've talked about. There's a couple other ones in here, like vertical angles and reflex angles. Those aren't really, I'm not going to test you on those, but if you're curious about what those things refer to, or you want to see a nice table with the definitions of and examples of the terms we do talk about, this is on page 595. Okay, and so now with these new terms, we can revisit some of the properties of our shapes and the relationships among them. And so they also provide this really nice table, which I'll zoom in on, of talking about, so basically when we remember, we start at level 0, and when we're learning about geometry, and we can holistically identify shapes. And then at level 1, we can start talking about different components of the shapes and recognizing some of their characteristics. And then at level 2, we're able to talk about the relationship that these things have. And so this is I like this chart because it kind of ties in all of these things, right? So it starts telling me about these different attributes or different qualities that the different components can have for each one of these different shapes. And it also allows you to kind of compare them across the different shapes so that you can see, both isosceles trapezoids and trapezoids, of course, have one pair of opposite sides that are parallel. And both rhombi, and parallelograms have two pairs that have opposite sides that are parallel. And so there are this is a nice way to kind of compare all of those different characteristics that they all have.